Right now, in the desert outside Phoenix, there is a building where the air is cleaner than a hospital operating room. And inside it, machines are printing structures a few atoms thick onto silicon. Nothing unusual so far, except for one detail. For the first time in more than a decade, the most advanced logic technology in production is not coming out of Taiwan. It's coming out of Arizona. Intel's VP and Director of Advanced Technology Programs, Chris Auth, put it bluntly. These are the most advanced semiconductor facilities not only in the US, but in the world. That is a massive claim, and my first instinct was to go and check it. So I did. And what I found is stranger and far more interesting than the headline because on one measurement, Intel is genuinely ahead of everybody on this planet, TSMC included, and on another measurement, it loses by roughly 30%. Both of those things are true at the same time. There is also one technology inside this node that literally no one else on Earth is manufacturing today, and it is not the transistor everyone keeps talking about. It sits on the other side of the wafer. This is the story of Intel 18A. What is actually inside it, where the claim holds, where it breaks, and what it means for the laptop you buy next, and for the AI running in your data center. Subscribe to the channel and let me explain. To understand why this matters, you first have to understand how bad it got. For most of computing history, Intel was the company, not one option among many. The benchmark everyone else was measured against. Then came 10 nanometer. Intel put it on the roadmap for 2016. It slipped. It slipped again. A single dual-core laptop chip trickled out in 2018 with its graphics disabled, which tells you everything about how that process was behaving. Real volume didn't arrive until 2019. And the server version didn't land until 2021. 5 years lost at the exact moment the industry was accelerating. And while Intel was stuck, TSMC quietly became the most important factory on the planet. Apple moved, then Nvidia, then AMD. And once you lose the leading edge, the damage compounds because the leading edge is where the money is. By the second quarter of 2024, Intel's foundry business pulled in $4.3 billion in revenue and posted an operating loss of $2.83 billion doing it. The company as a whole lost $1.61 billion that quarter and announced more than 15,000 job cuts. That is not a bad quarter. That is a company staring at the possibility that it no longer belongs at the front of its own industry. So Intel made a bet. In the summer of 2021, they announced a plan that sounded almost delusional at the time. 5 nodes in 4 years. Intel 7, Intel 4, Intel 3, 20A, and 18A, compressed into a sprint that would normally take most of a decade. And here's the part that usually gets skipped. They didn't actually deliver 5. In September 2024, Intel canceled 20A entirely and sent Arrow Lake to an external foundry so every remaining engineer, every tool, every hour could be pushed onto one node. 5 became 4. 18A was the finish line, and they crossed it. Now let's look at what they actually crossed it with, because there are 2 technologies in here, and together they represent the biggest change in how chips are built in over a decade. The first one is called RibbonFET. Quick explainer, no jargon. Every chip is made of billions of tiny switches, called transistors. A gate turns the switch on and off by controlling a channel that current flows through. For the last decade, that channel was a thin vertical wall of silicon with the gate wrapped around 3 sides. FinFET. It was brilliant, and it carried the entire industry from roughly 2011 until now. But 3 sides stops being enough when you are packing hundreds of millions of these into a single square millimeter. The gate loses grip on the channel. Current leaks when the switch is supposed to be off. Heat climbs, performance flattens. And there was a second problem, a physical one. To keep shrinking, the fin had to get thinner and taller. Imagine a wall of silicon a few nanometers thick standing 10 times its own width and height, And now imagine building billions of them without a single one leaning. At some point, you are not fighting electronics anymore. You are fighting structural engineering at the scale of atoms. RibbonFET is Intel's gate-all-around transistor, and the idea is exactly what it sounds like. Instead of touching 3 sides, the gate wraps completely around the channel. All 4 sides. Nothing escapes. And instead of one tall fin standing on edge, you get flat ribbons of silicon stacked horizontally on top of each other, supported from below, 4 of them per transistor in 18A. More surface contact means tighter control. Tighter control means less leakage. Less leakage means you can either run faster at the same power or run the same speed at dramatically less power. And in a world where AI models grind away in data centers 24 hours a day, that second option is worth more than almost anything else. But I want you to appreciate how hard this is to actually build, because the elegance of the diagram hides a nightmare. You don't carve those ribbons. You grow alternating layers of silicon and silicon germanium, stack them, pattern them, and then selectively dissolve away every germanium layer, so the silicon ribbons are left floating, suspended in space, held only at their ends. Then you have to grow the gate material into the gaps underneath them, gaps a few nanometers tall uniformly across an entire 300 millimeter wafer, billions of times. If the spacing drifts, performance drifts. If the gate doesn't fully wrap, you've built a defect that is buried under the structure where inspection can barely see it. That is the step where most manufacturers bleed yield. And it's the reason gate-all-around took the industry as long as it did. Now here's the detail I find genuinely clever, and it never makes the headlines. Intel built 8 distinct threshold voltages into 18A, 4 for NMOS, 4 for PMOS, spanning about 180 millivolts, tuned with dipole-based work function adjustments. Translation: the same process can produce a transistor optimized for a fanless laptop sipping a few watts and a transistor optimized for a 500-watt server chip screaming under a full AI workload. Normally, you would need to compromise. Here you don't. And that flexibility is exactly what a foundry needs if it wants to serve customers who all want something different. The numbers Intel published at the VLSI symposium hold up. Against Intel 3, the 18A node delivers 25% higher frequency at the same power, or 36% lower power at the same frequency. Over 30% more density, roughly a 1.3 times improvement, which works out to about 28% less area for the same design. The SRAM cell shrank from 0.024 square microns on Intel 4 down to 0.021. Pick whichever number matters for what you are building. They are all real gains. But what I like about RibbonFET isn't the numbers, it's the signal. The FinFET era is over. Every serious manufacturer is moving to gate-all-around, and this is the architecture your next GPU, your next phone, and your next laptop are all going to be built on. Intel simply got there first with a node actually shipping products, and that would already be a decent story. Except RibbonFET is the evolution. The revolution is happening on the back of the wafer, and this is where Intel is genuinely alone. Think about how a chip is wired. Every transistor needs 2 things: power to run and signals to tell it what to do. Traditionally, both of those travel through metal layers stacked on the front of the wafer, sharing the same real estate, competing for the same space. It's like running a highway and a water main through one pipe, and it gets worse every time you shrink. Because the wires shrink too, resistance climbs, and now your power delivery is fighting your signal routing for room that neither of them has. Power via takes the entire power delivery network and moves it to the back of the wafer. That's it. That's the idea. And the consequences are enormous. The front side is suddenly free for signal routing alone, so you can pack cells tighter. Intel measured an 8 to 10% transistor density gain purely from that reorganization, before you change a single transistor. The metal layers on the backside are far thicker than front side wires, which means much lower resistance, which means via resistance drops between 24 and 49% compared to Intel 3. And the metal layer RC performance improves by around 12%. Signals travel faster, timing improves, frequency goes up, but the most important number is a different one. Voltage droop improves by up to 10 times. Let me explain why that matters, because it sounds abstract until you connect it to something real. When a chip suddenly demands a burst of current, an AI inference request hitting all at once, a game loading a new scene, the voltage across the chip momentarily sags. That sag is droop, and because chips have to be designed to keep working at the bottom of that sag, droop forces you to run at lower frequency or higher voltage than you otherwise could. Kill the droop and you get that headroom back. Up to 10 times less droop is not a rounding error, that is design margin handed straight back to the architects. And the obvious question with anything this new is whether it survives contact with reality, because building on both sides of a wafer is not a small ask. You process the front side normally, drop tiny vias down through the silicon toward the transistors, then bond the whole thing to a carrier wafer, flip it over, and grind the original substrate away until what's left is a membrane a few hundred nanometers thick. Then you build the power network onto that. One wrong parameter in the thinning step and you have destroyed an entire wafer of finished transistors. This is also why people assume backside power would arrive years later than it did, and why the debug argument was so loud. Engineers had spent their whole careers probing chips from the front, and now the power grid is in the way. Intel's answer was to prove it on a real design first. Before it ever went into a product, they built a test chip that took the efficiency cores from a shipping architecture and rebuilt them with backside power. That test vehicle showed above 90% standard cell utilization and a roughly 6% frequency gain, and it debugged fine. Then they ran the production version through GDEC qualification. 1,000 hours of high temperature aging, 750 thermal cycles. It passed. This isn't a lab demo, it's inside the products you can buy right now. So here's the first loop closed, and it's the one that surprised me most. Chris Auth said it directly. Intel is the only one doing this in manufacturing today, not the only one who has announced it, the only one shipping it. TSMC's answer is called Super Power Rail, and it arrives with the A16 node. That node was originally targeted for late 2026. As of TSMC's 2026 roadmap update, A16 has moved to 2027. Samsung has talked about backside power for years and hasn't put it into a production node either. So Intel has a genuine dated structural lead on one of the most important architectural changes in modern chip making. And depending on how the schedules hold, that lead is somewhere between 1 and 2 years. Which brings us to the question everyone actually wants answered. Is 18A the most advanced node in the world or not? And here I want to be straight with you because the honest answer is more useful than a clean one. TSMC's N2 has been in volume production since late 2025. Both nodes exist, both are gate all around, so you have to compare them properly, and when you do, they split. On density, TSMC wins, and it isn't close. Analysts at Tech Insights measured high-density standard cell density at 313 million transistors per square millimeter for TSMC N2, against 238 million for Intel 18A and 231 million for Samsung. That's roughly 31% more transistors in the same area. SRAM tells the same story. Intel's 0.02 1 square micron cell gives about 31.8 megabits per square millimeter, while TSMC is at roughly 0.0175 square microns and around 38 megabits. More density means more function and less silicon means lower cost per chip and smaller dies for phones. That matters enormously. On performance and efficiency, the picture flips. Analyst scoring puts 18A ahead of both N2 and Samsung's SF2. Though I'd flag that these composite scores extrapolate from older nodes and the methodology is genuinely debated. What is not debated is backside power, and that is a structural advantage, not a scoring artifact. If your workload is a data center accelerator or a high-performance CPU, where sustained performance per watt is the whole game, 18A is a serious proposition. If you are building an ultra-dense mobile chip where every square millimeter is contested, TSMC still has the better answer. But there is a third number that decides more than either of those, and almost nobody brings it up: volume. Intel is currently running roughly 30,000 wafers per month on 18A across Fab 52 in Arizona and its Oregon facility in Hillsboro. Fab 52 alone is built for more than 10,000 wafer starts per week at full ramp, which is around 40,000 a month, and it is bigger and better equipped than TSMC's Arizona site, roughly double the wafer throughput of Fab 21's first phase. That is a real achievement on American soil. Now compare it to the whole. TSMC was at about 20,000 N2 wafers per month earlier this year and is targeting 100,000 per month by the end of 2026. So Intel can be technologically ahead on a specific axis and still be an order of magnitude behind on scale. Leading on paper and leading in volume are two completely different competitions, and Intel has only won one of them. Still, none of this means anything without products. So let's look at what has actually shipped, because this is where the story stops being a roadmap and starts being real. At CES in January 2026, Intel launched the Core Ultra Series 3, codenamed Panther Lake. First platform on 18A. Pre-orders on January 6th, systems on shelves on January 27th, and over 200 PC designs at launch. By the second quarter, that number had grown past 400 designs across consumer and commercial. The top configurations carry 16 CPU cores, 12 XE graphics cores, and 50 TOPS of NPU compute. Against Lunar Lake at the same 25-watt power level, Intel measured 60% better multi-threaded performance. In gaming, across 45 titles at 1080p high settings, 77% faster. And a reference laptop design hit 27 hours of video playback. A 60% generational jump in multi-threaded performance at the same power budget is not a tuning exercise. That is what a new node is supposed to buy you, and it is sitting in laptops you can walk into a store and buy today. And the AI numbers are where it gets interesting for anyone building at the edge rather than in a data center. On large language model work, Intel measured 1.9 times the performance of NVIDIA's Jetson Orin A GX 64 gigabytes. On end-to-end video analytics, 2.3 times better performance per watt per dollar. On vision language action models, the kind that drive robots, 4.5 times the throughput. That is not a laptop story anymore. That's a signal that the same silicon is being aimed at industrial systems, robotics, and everything else that needs serious inference without a rack behind it. Then came the server side, and this one is the more impressive engineering story. Intel unveiled Clearwater Forest at MWC in March 2026 and launched it as Xeon 6 Plus on June 1st. Up to 288 cores in a single socket. 576 megabytes of last level cache. And the way it's assembled is the interesting part. 12 compute tiles built on 18A, stacked using Foveros Direct 3D onto 3 base tiles built on Intel 3, with 2 I/O tiles on Intel 7, all tied together with EMIB. 3 different process nodes cooperating inside one package, plus 12 channels of DDR, 58000, 96 lanes of PCIe 5.0. in a 300 to 500 watt envelope. The performance follows: 17% more instructions per clock per core than the previous generation of efficiency cores. Against Sierra Forest, its own predecessor, Clearwater Forest delivers 2.26 times the average performance and 55% better performance per watt, doubling the core count inside the same 450 watt thermal budget. Against AMD's 192-core EPYC, Intel measured around 30% higher performance on average and roughly 1.3 times the performance per watt at typical utilization. And notice where the packaging happens. Fab 9 in New Mexico, the only high-volume Foveros 3D stacking facility in the United States. That detail matters more than it sounds because for years the standard complaint was that even chips made in America had to fly to Asia to be packaged. On this product, they don't. Now, here's where I have to be careful with you because internal products don't save a foundry. Customers do. And this is the part of the story that is still unfinished. Intel Foundry's numbers are improving and still ugly. In the second quarter of 2026, Foundry revenue was $5.8 billion, up 6% sequentially and up 31% year over year, with an operating loss of $2.1 billion. That loss narrowed by $348 million from the previous quarter, and it's a meaningful improvement over that $2.83 billion hole in 2024. But it is still a loss of over $2 billion in one quarter. And the number that really tells you where things stand is external foundry revenue, $293 million. That's how much of Intel's manufacturing is currently being bought by other companies on a $5.8 billion base. The factory is running mostly for Intel. The commitments do exist, though. Microsoft announced back in 2024 that it would build a chip design on Intel 18A. Amazon signed a multi-year framework that includes an AI fabric chip on the node. There are credible reports that Microsoft's next-generation Maya AI accelerator is heading to 18A or its enhanced variant, and separate reports that Apple has been evaluating Intel for the first time in years. And that enhanced variant is worth knowing about. In June 2026, Intel put 18A-P into production. Same design rules, same cell heights, so existing 18A designs port straight over, but with 9% more performance at the same power, or 18% lower power at 0.75 volts, and a 20 to 40% improvement in thermal resistance from a more aggressive wafer grinding process. For an AI accelerator trying to shed heat, that thermal number alone is a reason to look. And then there is the part of this story that has nothing to do with engineering. In August 2025, the US government took a 9.9% equity stake in Intel, $8.9 billion, 433.3 million shares at $20.47. Funded by converting $5.7 billion in remaining CHIPS Act grants, plus $3.2 billion from the Secure Enclave program. There is also a 5-year warrant for another 5% at $20 a share that only becomes exercisable if Intel stops owning at least 51% of its foundry business. Read that clause again because it tells you exactly what Washington is protecting. NVIDIA followed with $5 billion. SoftBank put in $2 billion. And that money lands on top of an already enormous private bet. Over the last 5 years, Intel has put $108 billion into capital and $79 billion into research. The majority of it aimed at U.S. manufacturing capacity, with more than $100 billion committed to expanding its American sites. Fab 52 in Arizona is the visible piece of that. Fab 62 next door is expected around 2028, with an infrastructure partner holding 49% of it, because at these numbers, even Intel doesn't want to carry the whole balance sheet alone. Why does a government do that? Because over 90% of the world's most advanced chips are manufactured in one place, and that place sits in the most contested strait on Earth. That is not a supply chain issue. That is a strategic dependency that every major government has been quietly panicking about for years. And you cannot fix it with subsidies alone, because a fab you subsidize into existence but nobody buys from is just an expensive building. You fix it by having a company on your own soil that can genuinely compete at the leading edge. Right now, exactly one company qualifies, and it is the one that was written off 18 months ago. So where does that leave us? Because I don't want to end this on a victory lap, and Intel isn't out of the woods. Start with yields, the number that decides everything in this industry. The entire business is how many working chips you get per wafer. Through 2025 and into early 2026, 18A yields were the single biggest question mark hanging over the company, and there were real reports that Panther Lake's profitability was suffering because of it. Independent industry analysts now report those problems as resolved, with defect density down into the range you'd expect from a maturing node, improving at roughly 7 to 8% a month. Intel's own leadership says 18A output ran 25% above target last quarter and grew 50% sequentially with yields ahead of plan. But Intel does not expect world-class yields until early 2027. That's the honest timeline. You can see the cost side of that too. Intel's CFO said they've driven the cost of the primary Panther Lake part down by roughly 50% year to date, with another 20% targeted. That's excellent progress, and it also tells you what that chip cost to make it launch. And the real exam isn't 18A at all, it's 14A. That's the node Intel needs external customers to commit to, and the commitments are due now. Customer decisions are expected to land from the second half of 2026 through the first half of 2027. The early signals are good. The 0.5 process design kit is complete. The 0.9 version is targeted for October. And Lip Bhutan says defect density and transistor performance on 14A are both outpacing where 18A was at the same stage. Risk production for internal products is planned for the second half of 2027 with high volume ramp in 2028. But the clock is not just technical. The 35% U.S. Advanced Manufacturing Investment Tax Credit expires on December 31st, 2026, which means construction has to begin before then to capture it. Meanwhile, Ohio, which broke ground in 2022, has slipped to 2030 or 2031. The German megafab and the Polish assembly plant were both canceled in 2025. Capital spending is guided above $20 billion for 2026 and significantly higher in 2027. This is a company spending enormous money on a bet that hasn't fully paid yet. And yet, look at what actually happened here. A company that was bleeding nearly $3 billion a quarter from its manufacturing arm that had lost the leading edge for the better part of a decade, that had to cancel one of its own nodes mid-sprint to save the next one, built a process with a transistor architecture the whole industry is copying and a power delivery scheme nobody else has managed to put into production. Not a slide, not a test chip. Laptops on shelves and 288-core servers and racks patterned in Arizona and Oregon and packaged in New Mexico. RibbonFET and PowerVia are not incremental updates. They are architectural shifts, and every competitor will eventually build something like both of them. Intel just got there first, and being first is the only thing this industry has ever really rewarded. Whether that turns into a business depends on things that haven't happened yet. Yields hitting world class in 2027, customers signing for 14A, and a foundry loss that has to keep shrinking every single quarter until it doesn't exist. What I keep coming back to is the shape of the thing. For the last 10 years, there was effectively one place on Earth you could go for the most advanced silicon. Now there are two. And competition at the leading edge is the single healthiest thing that could happen to computing, because it is the only force that has ever made these chips faster and cheaper at the same time. Chris Outh said volume production on 18A launches a decade of improvement on RibbonFET and PowerVia, pointing toward a target that sounds absurd until you look at the trend line. A laptop with 1 trillion transistors inside it. That's the direction. Whether Intel gets to lead the walk, there is still an open question. So here is what I'm curious about, and I want your take. Does technological leadership on one node actually matter if your competitor can produce 3 times as many wafers with it? Or does volume win in the end every single time? Drop your answer in the comment section below, because I genuinely don't think there's a settled answer to this one. And if you got something out of this episode, the best way to support it is to share it with someone who wrote Intel off 2 years ago and to subscribe to the channel.